Okay, and we're back. So here's what we were talking about last time. We were talking about the two-dimensional divergence theorem. And so what that says is that if you're interested in computing boundary flux, right, the amount of flux through a boundary, specifically outward through the boundary, you can compute that with a double integral over the interior, whatever the two-dimensional region is, whose boundary you're talking about, with the integrand being the divergence. So now how did we get this? And there are the calculations right here, a bunch of details preceding it in the notes, of course. We did this last time, so I'm just summarizing. And I'm going to say the heavy lifting, the bulk of the argument, where the magic happens, is this right here, Green's theorem. Right? Green's theorem is where we transition from a line integral to a double integral. That's phenomenal. That's extremely non-obvious, right? That these two, not only are these different integrals, they're different kinds of integrals, right? And the idea that those would be equal is a lot, right? That's a big statement. Everything that precedes is just kind of the rewriting the integral in different ways, and not really that much is happening. And everything that follows is just kind of computing by coordinates and recognizing what that integrand is, mostly details. So with this in mind, this two-dimensional divergence theorem is sometimes thought of as being, well, just a special case of Green's theorem. Right, again, here's Green's theorem. Green's theorem did most of the work, other than kind of turning everything sideways. I mean, again, most of it is just Green's theorem. All right, so with that said, now we did an example, or I guess I referred to the example last time. This is just plugging in, just a direct computation. I want to now give you a different point of view on the 2D divergence theorem. Not viewing it as a tweak of Green's theorem. Forget about Green's theorem. We're going to start all the way back at first principles, right? And I'm going to make the case that we can directly argue that boundary flux itself is another accumulating quantity, right? And remember, if you have an accumulating quantity, lots of immediate consequences follow. Well, then the whole is the sum of the parts. It behaves like a substance, independent of whether it actually is. Doesn't matter. It behaves like a substance. You can talk about its corresponding density, and you can compute it as an integral of that density, right? So all of that is just immediate once you can show it's an accumulating quantity. So let's make that argument. Here again, we have a two-dimensional region, sort of generic two-dimensional region, and let's talk about what does boundary flux look like. And of course, it's an integral around that boundary, and there's the convention: boundaries are always oriented outward, etc. So I'm going to represent that as drawing this boundary curve and indicating the orientations outward. Right, so there is the boundary flux computation that we would do for the hull. Now we need to show that the hull is the sum of the parts. Okay, so let's look at the left part. The outward oriented boundary flux there would be like so. Right, now let's look at the right part. For the right part, the outward-oriented boundary flux would be like so. All right, so here we have the hull, and we have the individual parts. Is the whole the sum of the parts? And again, at the quickest of careless glances, you would think, well, just clearly fails. Check out this thing in the middle. There's green and blue on this interior edge, but there's no purple. How could green plus blue equals purple? Look, there's green and blue, but no purple. Doesn't make any sense, right? But we do recognize that the blue tracks the purple along in here, and the green tracks the purple along in there. So canceling what we know cancels pretty immediately. We're left with this. This is our problem. This is our discrepancy. This is what's between us and being able to declare accumulation. And then we take a closer look at this problem and recognize that this is two flux integrals on the exact same curve, but with opposite orientations. This time, opposite orientations through the curve, as opposed to when we were talking about circulation, we had opposite orientations along the curve. Right? But again, there's two different directions along a curve, and there's two different directions through a curve. So different geometry, but still same curve, opposite orientations. They cancel. Everything disappears in a puff of smoke. And no discrepancy, no problem. And this is an accumulating quantity. Is that cool? Everybody all right with that? I personally think this is a much better way to think about the two-dimensional divergence theorem. Here, we're ultimately, most of the work is being done from a point of view of a kind of integral that we're not actually interested in. Using an operator that ultimately isn't the right operator. But because of how we set things up and the little 90-degree rotation, everything kind of works out. This is just very directly and bluntly, we have an accumulating quantity, and when you have an accumulating quantity, the whole of the sum of the parts n is an integral of a density. It's extremely relatable and familiar when we're talking about mass. We have very recently done this for boundary circulation, and I've pushed this idea correspondingly that curl is circulation density, because look at this, it's playing exactly the analogous role that mass density plays. Okay? And now, same thing, we have an accumulating quantity called flux, that is outward-oriented boundary flux, and same deal, double integral of flux density. How we doing? Is everybody okay? So I think this analogy is really very strong. By the way, let's just talk about these terms here. Of course, mass density, y'all are very familiar with that. Y'all have been talking about mass density probably since middle school or something, somewhere along in there. FYI, flux density. As much as I push this point of view of thinking about these things in terms of accumulating quantities and corresponding densities, this term is extremely common. In fact, in my physics classes as an undergrad, I heard my physics professors say the term flux density more than I heard them say the term divergence. Right, they would write del dot F, and in class they would say double integral of flux density dA. Right, so this is a very, very common point of view. As it should be. Again, it could not be more natural. This is a density. It's something I'm multiplying by size to get stuff. The stuff being flux makes sense to call this flux density in the same way that up here when you're talking about mass, the stuff is mass and we call it mass density. So I think this term is extremely natural. It's extremely communicative of what it is and how it behaves. What role does it play in the theorems? And very happy about the fact that it's also very, very common. Okay, how are we doing? Okay. Now, for whatever it's worth, this term, circulation density, much less common. I think that's unfortunate. It's just as natural. Right? Thinking of curl as circulation density is totally analogous and just as natural as thinking of divergence as flux density. For some reason, I don't know, it just happens to be. It's just not in as common of a use. There is a different term that I've recently... I'm at the point where anything in the last 10 years is recent, right? But fairly recently, in some sense, I started hearing a related term, vorticity, which first of all sounds really cool, right? It sounds sophisticated and complicated, makes you sound smart, right? But also pretty natural. Let's think about the what is it that curl actually does, and it's telling you to what extent circulation, which is a measurement of how much the fluid has sort of a rotational aspect to it, to what extent is there a rotational element to the fluid. Well, I don't know if y'all are familiar with the term vortex, right? But it means something that's rotating. It's also a really cool term. Personally, I like the term circulation density a little bit better, but be aware of the term vorticity. Okay. All right. Moving along. Let's talk about the fundamental theorem of calculus. Now, I know y'all know the fundamental theorem of calculus. I'm not here to teach you about the fundamental theorem of calculus exactly, but we are in a situation, and I've done this several times, and y'all know this is I like to do this kind of thing. If there is a point of view on something familiar, if we point out that perspective on the topic that you already understand, then that will help you sort of learn by analogy. You can think, okay, well, the multivariable version, it's just like that single variable version, just in a different setting, right? So I'm going to give you a particular take on the fundamental theorem of calculus that I'll bet you haven't seen before. I think is extremely valuable in this sort of analogy, learning by analogy sense. And here it is. It is an accumulation theorem. It's kind of like Green's theorem and the 2D divergence theorem in that sense. There is an accumulating quantity in play. And it's what you might call the left side of the equation, right? When you write down the fundamental theorem of calculus, there's an f of b minus f of a. That says how much does f change over the interval from a to b. Given that one-dimensional interval, on that interval, how much does f change? And change is an accumulating quantity. Now let me try to persuade you of that. Why is change an accumulating quantity? I'm going to skip over some stuff and then come back to it. Here's a picture. We've got some function. And you can see it's defined on the interval from a to b. Let me highlight just let's see, how am I going to do that? Let me do it about like this. Here's my interval from a to b. And how much the function changes on the interval from a to b. Well, it starts at f of a, it ends at f of b. There's the corresponding change. Now, remember what an accumulation is. An accumulation means that if you look at a disjoint union of intervals in this case, we would need for the corresponding quantities to add. Right? We need disjoint unions to add. Okay, so here's what I'm going to do. I'm going to look at this purple interval as being a disjoint union of that green interval and this blue interval. Right, now just for sort of visual aid purposes, I'm going to look at this point C that's sort of, sandwiched in between them, and I just need to be able to make a reference to what the value of the function is there, and it's something like that. Okay, so is green plus blue equal to purple? Well, let's see here. How much does f change on the green interval? There it is. How much does f change on the blue interval? There it is. And sure enough, as it's supposed to, purple being the disjoint union of green and blue here, is purple equal to green plus blue? Well, of course it is. That makes sense to everybody? Everybody happy? Well, we've got an accumulating quantity. That means blah, 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 the usual line of stuff. And the final punchline of which then is that we can think of this accumulating quantity, namely change. We can think of that as an accumulation, whole sum of the parts, yada, yada, yada. There's a corresponding density. And of course, now we know what the answer is. We know what the integral that computes change. We know that's the integral of the derivative. That's just, again, Calc 1, right? Fundamental theorem of calculus. And so that corresponding density is the derivative. And this is probably, I assume, a new take for y'all on what a derivative is. I'll bet you've seen previously that a derivative is a slope. You've seen previously that it's a rate of change. You might have even heard it described as a sensitivity. I think that's an interesting take, sensitivity, because depending on how much you change the input, correspondingly how much the resulting change in the output. It's a nice point of view. Probably your first time hearing of this is a density. Let me explain why I think that's perfectly reasonable in the context of the picture. You know the derivative is the slope of the graph. Wait a minute, let me get it into pencil mode. There's a little piece of the graph. It's so hard to write on this thing. That's better. A piece of the graph. Rise over the run. Right? And looking at that rise over a run, let's see here. What color can I use? The rise, how much the function increases there, that rise is the change. That's how much the function changed on that little subinterval. The run is, let's see here, colors. Use gray. The run is the size. How big is that little subinterval? You can think of it as rise over run, aka slope, and you all got great intuition for how the slope of the line relates to the derivative. Totally different take, though, is it's literally this accumulating quantity called change per unit size of the interval on which it has changed, and stuff per unit size is density. What do you think? Weird take, right? Okay, so now that we've got that established, let's talk about what the benefit of this is. I mean, why do we need to think about the fundamental theorem of calculus in a totally new and different way? What's wrong with what we were doing, the way we were thinking about it previously? There's nothing wrong with how we were thinking about it previously. But here's what you can do with this. If I were to reconsider, let's go all the way back to, let's see, where's my picture? Well, let's just look at this picture right here. This is the first example that we did. And the question was to compute this line integral. Right, going around that way. That line integral is computed on the boundary. Well, of course it is. That's what it is. It's computed on the boundary. And I make this kind of implausible suggestion that, well, even though we compute it on the boundary, I'm making the claim that you can think of that as actually sort of happening in the interior. We compute it on the boundary, but I'm claiming that where it really is, where it's coming from, if you will, is in the interior, because it's a kind of a stuff, and stuff is distributed over that interior. And a very reasonable reaction to that suggestion is, what are you talking about? How could you possibly suggest? It's clearly computed right here on the boundary. It's not in the interior. Show me in this integral here where I look in the interior. I'm not looking in the interior at all. Right? Outrageous suggestion that something computed on the boundary is actually happening in the interior. Right? And I think that's a perfectly reasonable complaint. Let's make that same complaint here with the fundamental theorem. Totally analogous theorem, also an accumulation theorem, also with the density, etc., etc. Where do we compute change? We compute change by looking at the endpoints, aka the boundary of our interval. But if I were to ask you to believe that, yeah, even though we computed on the boundary, it's actually happening in the interior, and more specifically, even in this specific subset of the interior, no shocker. Right? In fact, you can literally see the function changing. right? There's nothing weird about that at all. The total change between A and B, computed at A and at B, computed entirely on the boundary. Well, of course it happens in the interior. That's how stuff changes, right? It changes as in the interior you move from A to B. Nothing weird at all. So what I'm going to encourage y'all to do, I think this is a good sort of mental exercise. Try to take whatever comfort you have with the idea that stuff changes in the interior, right? And recognize that that's really all I'm asking for you to believe when I say that circulation happens in the interior as well. This sort of like very hard to imagine thing in this context, it's really not that different from this very easy to imagine thing here. Does that make sense to everybody? Something to chew on, to think about. Okay, here's the second nice thing about this, and that is that if we look at the derivative, let's see here, here we go, f prime, right? I claim the derivative tells us not only that the function is changing in the interior, it tells us where and how much. Right? So, for example, at a point like this, there's a lot of change happening. It's right there in the picture. I mean, look how steep it is there, right? That at this point, there's a lot of change happening. Okay, now let me quibble with my language. I mean, technically, at a point, at the single point, there is the value of the function at that single point is a single value. Technically, there's no change happening at a single point. But, okay, yeah, sure. But when I say the change that's happening at a point, what I mean is in the general vicinity. As if I look at a small interval around, some little neighborhood of that point, yeah, then there's a lot of change happening. So when I say how much change is happening at a point, we mean what is the change per unit size? What is the density? Right? So the derivative tells me there's a lot of change happening near that point, and it tells me that there's quite a bit less, but still some change happening at this point. The value of that density tells me what I can comfortably see from the picture here, that there's less change happening at that point, more change happening at that point. And by the way, zero change happening at that point. Well, I claim that something very similar is true of curl and divergence also, right? Those are the densities for the Green's theorem and for the 2D divergence theorem, and they likewise are going to tell us where and how much the function is changing. Real quick example, by the way, before we abandon the single variable case. Let me just point out explicitly, we've got an example here. Here's a function, interval from 0 to 3, total change is 9. Okay, how much of that change is happening at the point x equals 1? Right, how much of the change is happening there versus how much is the change of the change is happening here at x equals 2? And obviously, again, when I say how much change is happening at a point, I mean near the point. Right? Well, the job is done for us by our density. Change density, which is the derivative, which is easy to compute. And you could just straight up compute it at x equals 1 and at x equals 2. And, well, the derivative is clearly greater at x equals 2, between these two options anyway. So it's greater when x equals 2. The derivative is the change density. The derivative is telling me where the change is happening, so more change is happening at 2. Which, again, perfectly obvious from the picture. Okay. So I claim that what's nice about this is that this is kind of a roadmap to how to make sense out of curl and how to make sense out of divergence. They too are telling you how much of the corresponding quantities are actually happening near a given point. And it's just that it's harder to see when you're talking about something like this. And, now in this case, I've deliberately drawn a vector field where it's reasonably under control vector field, right? Nothing too wacky. It's constant down here, right? In this sort of, below the gray area, and it's constant up here above the gray area, and it's sort of continuously changing in the gray area from the short field vectors up there, continually growing down to the larger field vectors down here. So this is ultimately a pretty simple vector field. Hard to write down the formula just because it's sort of behaving differently in 3 different zones, but whatever. In most cases, it's really hard to look at your picture and see where circulation is happening. But in this case, it's actually pretty straightforward. Imagine, for example, y'all remember I like to visualize circulation as how do leaves floating in the fluid, how do they rotate? So here's a little leaf. Let's plop that leaf down right there. And now, of course, the water flow, let's think of the vector field as being a flow of water. The flow is going to make that leaf go to the right. Of course it is. But as it goes to the right, how much will it be rotating? Is that leaf going to be spinning as it goes downstream? And I say it's not, right? Look what the vector field is doing. Our vector field is pushing it kind of the same on both sides. It's just going to translate along to the right. There's no rotation. No rotation means there's no circulation density there. Okay, what about a leaf, let's say there? And here's a different story. Now that leaf is still, of course, going to be flowing downstream. Well, of course it is. But let's think, though, is it going to be rotating? And, well, it's being pushed on sort of the top side, but it's being pushed even harder on the bottom side. And just like when you're at the grocery store, if you don't hold on to both ends of your grocery cart, if you only hold on to the right end, you push just from the right, well, that grocery cart's going to turn to the left, isn't it? Right? Same thing here, right? Because it's being pushed harder on the one side, this leaf, as it goes downstream, is going to be turning. It's going to be rotating. And so let's see here, something kind of like that. I think it's going to be a counterclockwise rotation. Does everybody buy that? So we can see that. Now, what would happen if I computed curl? Now, again, I don't have a formula for this, but if you were to compute curl, here's what would happen. You would find that in this region up here and in this region down here, where we've already agreed there's no rotation happening, right? Well, here's the thing. Curl up there, curl of F would be 0. And likewise down there. Whereas in this region along in here, if you were to compute the curl, if we were to have a formula for this F, and if we were to compute the curl would be positive. Keep in mind the convention. Curl is based on circulation. Circulation is defined in terms of, in terms of boundaries. Boundaries are defined according to a certain convention. We're counterclockwise, arbitrary but standard. So counterclockwise rotations are the sort of the default standard positive. So positive because the leaves are turning counterclockwise. And so again, just like with the derivative, in the same way that here the derivative by being positive here, even bigger here, and 0 there. The derivative is telling me where this change that I see on the boundary, where is that change happening? Well, a lot of it's happening along in here, right? The derivative points right to where that change is actually happening in the interior. Likewise, curl tells you where the boundary circulation that you see on the boundary is actually happening, right? So we've got a certain amount of boundary circulation happening around that boundary. We measure it on the boundary, we visualize it as being on the boundary, but honestly, it's coming from the fact that the little leaves inside of this gray area are rotating counterclockwise. That's why, in some reasonable sense, you're getting a positive amount of circulation there. How are we doing? Okay. Likewise with flux, by the way, same basic story. It's a little bit different of a picture, but same basic idea. We look at this boundary here, keeping in mind boundaries are always oriented outward. That's our convention, right? And you can talk about how much outward oriented boundary flux this vector field gives you. Now notice I've crafted a different vector field to again make things work out really nicely. So where's that flux coming from? Well, if I were to look at a little region like this, little region like that is what's the outward oriented boundary flux on this orange square? And I'd say it's going to be 0. There's the same amount of inward flux as there is outward flux. So in the net, we have a negative outward flux on the left because it's inward. We have a positive outward flux on the right because it literally is outward. Adds up to 0, no flux. And guess what? If you were to compute the divergence, if you were to compute the divergence here, you would get 0. Whereas, by contrast, if you were to look at a region like this, well, now this, there's some inward and some outward at the same time. But you see how in this gray area, the field strength is increasing as we move to the right. So, on that left edge, yeah, it's a negative outward, aka inward, negative outward flux on that edge. And yeah, it's a positive outward flux on this edge. The positive one's just that little bit bigger. And so altogether there is a positive amount of flux happening there. Right? And if you were to compute the divergence, indeed, you would find that that is positive. So again, our density, in this case divergence, because we're talking about flux, the density tells you where the change that you're witnessing on the boundary, the flux, the accumulating quantity, right? The flux that you're witnessing on the boundary, this is telling you where it's happening and how much and where it's not happening. How are we doing? Is everybody with me? Is it all cool? Questions? Feel free. And I think it's really important to be able to visualize these things. I mean, the formulas are in the book. Y'all can read the book, right? I mean, what I feel like I can offer here is geometric intuition for how do I think about this? What does it look like? Stuff like that. And which really does help with problem solving and being able to make use, practical use of these ideas, in the field. You can make all this quantified. Here's some computations. No tricky curves here. This is just a rip-off of this example. Here, we looked at an explicit function. We asked, where is the change happening? And we used change density to figure that out. Here, we have a vector field. We have a rectangle on which we can talk about boundary flux and boundary circulation and question, is there more flux happening at this point or that point? Is there more circulation happening at this point or that point? in the interiors. And again, you use the densities. If you want to know where the circulation is happening, you use circulation density, aka curl, which you can totally compute. And then you just see where it's greater. If you want to know where there's more circulation happening, you look at circulation density. It would seem here, look at the numbers, it seems like there's more happening at 2, 4. But the density is greater there. Likewise, if you want to know where there's more flux happening, we're going to look at flux density, aka divergence, which again, you can just compute. We've got formulas, very convenient formulas. You compute that divergence. You plug in the 2 points we're interested in. Where is there more? Where is the divergence greater? Where is there more flux happening? Well, it would appear to be this point, 3, 3. All right, so a lot to think about. I hope y'all will find it as useful as I have to think about how. Let me get to this. How divergence and curl are just playing the role of the derivative, right? In these various different theorems. And again, there's I think I'm repeating myself at this point, so I'm going to just go ahead and move along. Okay. I did say when I wrote down Green's theorem, or I wrote that problems come up if there's a singularity in the vector field. Singularity means a point where the vector field's not defined. Take a look at this vector field right here. We have a pretty serious problem if you're looking at the origin, which makes that denominator 0, and you can't divide by 0. Not even 0. You can't divide 0 by 0. Nothing can you divide by 0, right? So the vector field fails to be defined at that singularity. That's going to mess up a lot of stuff. So let's see how our theorem fails, and then let's see how might we fix it. How might we kind of patch together kind of a hacked replacement concept. Okay, so here we go. Let's compute the curl. Y'all can compute for yourselves. If you take the curl of that vector field, turns out you get 0, at least the formula. You compute the curl and you get 0. Now, of course, that's only valid away from the origin. At the origin, there is no vector field. Doesn't matter what the symbols say, right? If the vector field's not defined, then you can't talk about any partial derivatives of it. So at the origin, we do still have this problem. But that's pretty cool result that the curl is 0, right? So the curl is 0 everywhere except the origin. And again, at the origin, something mysterious is happening that we don't understand. Okay. All right, well, let's take a sloppy take on this first. Let's ask, kind of sloppy and careless, how would I compute this line integral around what I've written here as C2? How would I compute that line integral? And it's tempting to say, well, line integral, circulation, boundary circulation. Well, I would compute it as a double integral of curl. And we'd look at the interior region here and say, well, gosh, in this entire interior region, the curl is 0. And oh my gosh, that's a one little annoying point. It's just a one little point. Come on, how much difference could that one little point possibly make? It would seem. Again, we're in careless and sloppy mode right now, right? Well, it seems like it wouldn't make that much of a difference, and if that's the case, we're integrating a bunch of zeros here, it would seem, and you would maybe kind of expect that the answer would be 0. And that's, as it turns out, wrong. Green's theorem does not apply here. Green's theorem is very delicate. Green's theorem doesn't apply at all if there is a singularity. It just doesn't work. And I can show you why it doesn't work. We're going to witness it fail by actually computing these line integrals. And again, let's back to, looking at this line integral, and I'm going to start by thinking about for that curve there, or something along those lines. So it turns out that for that curve, the answer is 2 pi, which is not 0. And I'm going to show you how you can prove that, how you can compute that. Just as a starter example, I would encourage you to start with literally the unit circle, right? Any circle centered at the origin. And that you can straight up parameterize. You could totally just pull back through the parameterization, plug and chug, chapter 5 style, and compute that out, and you will get 2 pi. And here's the better calculation, but by the way, good exercise, and I hope everybody will do that, right? Everyone should do that once in their lives. Here's the better way to do it. Y'all remember this equation, right? That's from polar coordinates. Take the differential of both sides, and it turns out what you will get, you can rewrite at least into this form, that the thing we're keeping track of as I compute that integral, as I go around my path, I'm just keeping track of how much theta changes. As it turns out, it's very not obvious until you do the calculation. But what we're doing is we're just adding up a bunch of little changes of the polar coordinate theta. Right? And so once you make that realization, well, then it's actually pretty immediate. How much does theta change as I go around a loop like that? Well, theta starts at 0, and then it goes all the way around to 2 pi. And if you were to go around twice, okay, bear with me here as I try to, you're to go around twice. How much did theta change as you went around twice? Well, theta increased by 4 pi. Whatever the number of times is that you go around counterclockwise, that's what you multiply by 2 pi. K is the number of turns. By the way, we call K the winding number of the curve. FYI. How are we doing so far? I still haven't resolved the concern, but at least we've shown that the integral's not 0, or at least it's not necessarily 0. Is that cool, everybody, so far? Okay. All right. So, can I recover any sort of version of Green's theorem, or at least this idea that circulation somehow kind of accumulates over the interior? And turns out you totally can. There's a really nice takeaway on this. So, it's kind of like at the origin, it's kind of like there is a discrete lump of circulation. I know that sounds super weird, a lump of circulation. Let me just remind you, we've talked about how circulation is an accumulating quantity. That means it behaves like a stuff. It behaves like a substance. Substances, like mass, people can talk about a point mass, and no one freaks out. Right? It's not physical. There is no such thing as an actual point mass. But if you have a teeny tiny itty bitty little thing that has all of the mass relevant to the problem, it's convenient to think of it as being at a geometric point. Right? So point mass. And I'm just saying same thing. It's just that it's not mass. It's a different kind of a substance now. Now I'm saying that it's like there is this substance called circulation. There is a point-sized lump of that stuff, if you will. Again, this is just how to think about it. That is at the origin. And let's think about, with that point of view in mind, can I make sense out of this line integral being 2 pi? can I make sense out of this now as we're just adding up however much circulation is on the inside there? Well, yeah, because on the inside there's no circulation density anywhere except at the point where we have a lump, a 2 pi lump of this stuff called circulation, and that's where that 2 pi comes from. It comes from that lump in the interior. That's a take, right? That's a point of view, and it works with any curve that you might want to talk about. So, for example, let's look at this other curve I have drawn on here. That curve there, and let's remind ourselves that closed curve has an interior. And that interior is kind of like this. Now, let's talk about what the actual value of the line integral is. The actual value of this line integral for this curve, for that curve there, well, we have to keep track of how theta changes, how many times, if I go along this dark blue curve, how many times do I go around the origin? I don't go around the origin. I fake it. I go a little ways as if I'm going around the origin, but then I come right back, and theta's back down to 0 again when I get to here. And then theta starts to go negative, and it looks like I might be going the other way around, but then nope, and it starts to increase again, and again, right back to 0. Theta doesn't change at all as you move around this curve. Because the curve does not go around the origin. Said differently, the origin is not in the interior of this region. And so again, thinking about circulation as being an accumulation of this stuff, this substance called circulation, and there being a lump right there, yeah, but that lump's not in the interior. There is no circulation in the interior. The lump of circulation is out of the interior, so when you do the double integral over this interior, 0. Which again, correct answer. Right, because for this curve, we just agreed this integral is 0. It's kind of perfect. Does that make sense to everybody? Okay, so this kind of thing is a helpful sort of little bit of intuition for thinking about how to deal with singularities in certain cases, and unfortunately it's not always quite this simple. It worked out, I deliberately arranged it to work out nicely here, but common analogous scenarios that y'all will see. We're going to see an analogous situation when we're talking about vector fields, gravitational vector fields, for example, and electric fields. Big deal for you engineers, right? Electric fields, they're in everything, right? And how do you understand electric fields? How do you relate to point charges? Well, point charges create singularities in the electric field, and the way that we deal with those singularities is highly analogous to what we just did here. So this is kind of a first step. And we'll come back, we'll talk about the equivalent, sort of the analogous version of this for electric fields in the next couple of weeks at some point. Okay. All right, real quick, last thing I'm going to throw at y'all before we call it a day. We'll just get started on section 6.3. We have this theorem called the fundamental theorem of line integrals. Kind of smacks of the fundamental theorem of calculus, doesn't it? F of B minus F of A. Oh my gosh, it's like totally the same thing, right? Very, very similar. Well, absolutely. And by the way, the analogy continues with, notice that the integrand is a derivative of sorts. It's a gradient. And notice that the thing that I evaluate on the other side is the anti-gradient. Just like with the fundamental theorem of calculus, it would be the antiderivative. So it's structurally super analogous to the fundamental theorem of calculus. Right? By the way, real quick comment, FYI, physicists like to call a vector field that is a gradient, they like to call it conservative. So heads up, be aware, you're probably going to hear that term a lot. My personal preference is if a vector field is a gradient, I like to call it a gradient. It's right there, right? Low-hanging fruit, right? Why not? But anyway, it does make sense. This does make sense if you're talking about conservation of energy. Gravitational fields being gradients allow us to create this concept called potential energy. And it's only because you have the concept of potential energy that you can talk about conservation of energy in the potential versus kinetic sense. So anyway, strong analogy. We're out of time. We'll pick up here later. See y'all later. Have a good one.